はい、始めたいと思います。これでうまくいってると思うんだけど。私は、古賀先生で、ツイッターで、主にツイッターで古賀先生でやってます。それで、コンパスの方に、ページがあります。このコンパスで、申し込みしてください。で、コンパスの方で、ここに資料っていうとこ、あるいは、ちょっと待ってね、ツイッターから行くと、このブルーキャットでページがあります。で、このサスキンド、レオナルド・サスキンド、アート・フリードマン著の、クォンタム・メカニクス・ザ・セオレティカル・ミニマムというのを読んでいます。それで、ブルーキャットのページでは、ここにテキスト PDF はここにありますっていうところにあります。あるいは、コンパスの方では、このテキスト in PDF、今日はちょっとコンパスの方でいきます。テキスト in PDF というのをクリックすると、ギガファイルに行くので、これをこうクリックすると、ダウンロードできます。で、このくるくる表示を回せば、今日は何ページからだっけ、295ページからやります。いいかな、よろしいでしょうか。特に問題ないと思うんだけど、30ページあたりかな。295ページのこの辺からやりますと。良いでしょうか。それで、ハッシュタグサスキンド QM、ハッシュタグサスキンド QM というのを、クリックしていただければ、出てきます。それで最新のやつを見れば、あれおかしいな、なんでこれ最新なの、今送ったやつが出てきます。そうだ、その前に、明日、次回に関しては3月6日、日曜日9時からということになるかと思います。それで、というのは、これまだ締め切ってないのかな。一応明日のこのアンケート、まだ締め切ってないみたいですけども、得票0票なので、日曜日の9時から、夜の9時からというのが得票1票あるので、確定だと思います。それで月曜日に関しても、9時、10時、11時というふうに入れられるようになっています。これなんだまた明日になればこの先の部分を付け加えたいと思います。もしツイッターを使ってない人は、コンパスのフィールドか、ブルーキャットのフィールド などで、あるいは YouTube へのコメントなどで、私に連絡をいただければ、その枠で開催したいと思います。それで YouTube は、あれこれダメか。YouTube を見てみると、などで、あるいは YouTube へのコメントなど、0人参加です。YouTube に関しては、どうするか。例えばこういう古いのを開くと、ここの、概要のとこにコンパスとブルーキャットのリンクをつけてますので、YouTube の概要のところから、コンパスへ飛べば、これまでの7回分の、リンクがここにあります。あるいは、ブルーキャットに飛んでも、ブルーキャットの中にもこうやって7回分のリンクがあります。それで、あとは、これサスキンの QM っていうのを、あれいけないのかな。サスキンの QM っていうのを押せば、こういうふうに出てきます。これなんだ ?1、2、3、4。なんで4つしか出てこないんだ。なんで4つしか出てこないのかわかんないですけど、出てきます。それから、ここのコメント欄に、私に対するコメントあるいは質問などを入れていただければ、読むことができると思います。ということで 9.7 リニアモーション&クラシカルリミットということをやります。You might think that we have proved that the expectation value of x exactly follows the classical trajectory, but what we've actually proved is quite different. ちょっと待ってね。こっちはあれか。リツイートは言ってないね。言ってないですけど、大丈夫だと思う。3月5日21時。はいはい。But what we've actually proved is quite different. The difference exists because the average of a function of x is not the same as the function of the average of x. Function of the average of x. If equation 9.18 had read ddt expectation p equal minus dvdx, this is wrong. What is correct is this is correct. Minus dv dx expectation value. So this is correct. In quantum mechanics. This is wrong in quantum mechanics. Okay, so let me emphasize, it does not. Equation 918 does not read this. It does not read this, but it does read this. It's complicated. Anyway, then indeed we would say that the average position and momentum satisfy the classical equations. But in reality, the classical equations are only approximations. Good whenever we can replace the average of dvdt. That's this. Average of dvdx is this. If we can replace this by the function of the average of x, so if you can replace this by this, then classical mechanics holds. When is it reasonable to do this? The answer is whenever the Vx varies slowly compared to the size of the wave pocket. If V varies rapidly across the wave pocket, the classical approximation will break down. In fact, in that situation, a nice narrow wave pocket will get broken up into a badly scattered waves that has no resemblance to the original wave pocket. The probability function will also get scattered. Then you will have no choice but to solve the Schrödinger equation. You will have no choice to use Heisenberg equation of motion, but you will have to solve the Schrödinger equation directly. Let's look at this point more closely. Mathematically, we've made no assumptions about the shape of our wave pockets, but we have tacitly暗黙のうちに We have tacitly thought of them as being nicely shaped function with a single maximum smoothly trailing off to zero in the positive and negative direction. This condition, though not explicit in our mathematical assumptions, does have a real impact on whether a particle behaves the way classical mechanics would lead us to expect. So, then there is a more explanation. Bimodal, two-humped function centered at x equals 0. Note that expectation value of x is 0, but uncertainty of x is larger than 0. To illustrate this point, let's consider a slightly weird, 変な slightly weird wave pocket. Figure 9.3 shows a bimodal wave pockets having two maxima centered at the origin of the x-axis. Now, let's consider some function of x, say fx, where f represents force. The expectation value of fx is not the same as the function f of the expectation value of x. In other words, fx expectation is not f of expectation value of x. The right hand side is a function of the center of the wave pocket. It is not the same as the left hand side, which correspond to our results from the previous section. F expectation value has the same form as the right hand side of equation 916. Okay, this is just f x expectation. But what is number 5? We call that the same thing. Yeah. This is called potential energy theorem. Let me give you an example where these two expressions could be extremely different. Suppose that f is equal to x squared. And suppose the wave pocket looks like figure 9.3. What's the expectation value of x? It's 0. And so is f of expectation value of x. And so means 0. So expectation value of x is 0, then f of expectation value x is also 0, because f of 0 is 0 square equals 0. On the other hand, what is the expectation value of x squared? It's greater than 0. What is the expectation value of x squared? It is greater than 0. So, when a wave pocket is not a nice single bump, that is mainly characterized by its center, it is not always true that the time rate of change of the momentum is the force evaluated at the expectation value of x. It's only when the wave function is concentrated over a very narrow range that the expectation value of f of x is the same as f of expectation value of x. So we have cheated a little in saying our quantum equation of motion looks classical. That depends on the wave packet being coherent and well localized. That depends on the wave packet being coherent and well localized. Everything else being equal. When the mass of particle is large, but is equal, the wave function tends to be very well concentrated. Everything else I don't understand. Everything else being equal. When the mass of particle is large, the wave function tends to be very well concentrated. I don't understand this. Everything else being equal. If there are no very sharp spikes in the potential function v of x, then it will be a good approximation to replace expectation value of f of x with f of expectation value of x when v of x has spikes. However, the wave packet tends to break up. For example, suppose we have a nice wave packet moving to the right and it hits a point structure like an atom with a potential function similar to 9.4 with figure 9.4. This one, spiky potential function. Potential functions with sharp peaks tend to cause wave functions to scatter. The smaller these features are in relation to the wave packet, smaller means narrower width, the more the wave packet will scatter, and the less classical it will become. Difficult English. The smaller these features are, smaller means narrow. The narrower these features are in relation to the wave packet, the more the wave packet will scatter, and the less classical it will become. Okay, anyway. Similar to figure 9.4, the wave packet will spread out and disintegrate. If, on the other hand, it hits a very smooth potential, then it will go through the smooth potential, moving more or less according to the classical equations of motion. We don't expect quantum mechanics to reproduce classical mechanics in every possible circumstances. In some possible circumstances, quantum mechanics does not reproduce classical mechanics. we expect it to reproduce classical mechanics in circumstances where it should. Where the particles are heavy, potentials are smooth, and nothing causes the wave function to disintegrate or scatter. Number 6. Not as eloquent as Garrison Keillor's tagline, but true all the same. Don't worry, I don't understand here. And I don't understand this. Don't worry. Don't worry. What physical situations leads to bad potentials, but that break up the wave function? Suppose a potential has features that have a certain size associated with them. Think of figure 9.4 on steroids, with lots of large closely packed spikes. Steroids. Think of figure 9.4 on steroids. Steroids. Steroid. Steroids with lots of large closely packed spikes. なんじゃこれ? Suppose we call the size of these features delta x, and that delta x is significantly smaller than the incoming particle uncertainty in position. Delta x is smaller than delta x. If the sharp features of Vx exist on a scale that is much smaller than the size of incoming wave packet, the packet will break into a lot of little pieces. Each one will scatter off in a different directions. Roughly speaking, when the features of the potential are shorter than the wavelengths of the incoming particle, the wave function will tend to break up. Don't understand. Think of figure 9.4 on steroids, with lots of large, closely packed spikes. Not so sure. I'm not so sure. Steroids. It may be this meaning. Okay, it may be you have a spike like this. Spike かける。なんでかける？ローディング。Something is wrong. Okay. So maybe spike. Something is wrong. I don't understand. Hey. What's wrong? Okay, spike.あ、書けないじゃん。なんだ俺。書けません。I think it should be a spike. Something like this. And your wave function is something like this. So this, let me see. Yeah, okay. Your wave function is pocket. So this is pretty wide. This is like delta x. And within this envelope, you have wave like this. This is called wave pocket. And now your spike size is delta x. So this width of spike is smaller than uncertainty of your wave. Okay. In this condition, your wave just scatter crazy. So this is more like, see, this situation is more like this. Okay, you have water. So there is like how do you call it? Kui is this one. So then if your wave, this is like water surface. Then after your water wave hit this one, kui, your wave becoming like this. Because this is a wave wavelength is larger than the diameter of kui. Yeah, then your wave spread out. I think this situation is the same. In quantum mechanics, the particle is a wave. Okay, then the size of this particle is delta x, capital delta x. Okay, then if your potential has spikes with the width small delta x, and this width of spike is very narrow, and potential is very large, then your wave scatter away. So your wave is disintegrate, jammed. Okay, that's the thing. That's what this says. I think. I don't know what he means by steroid. Anyway, if the sharp features of Vx exist on a scale that is much smaller than the size of incoming wave packet, the packet will break into a lot of little pieces. Each one will scatter off in a different direction. Roughly speaking, when the features of the potential are shorter than the wavelengths of the incoming particle, the wave function will tend to break up. Let's say you take a bowling ball and ask, what is delta x? We can use the uncertainty principle to gain some intuition about this question. Typically, delta p times delta x is bigger than h bar. But in many reasonable cases, it is of order h bar. Now, P is about as concentrated as it can be. But for ordinary macroscopic object, what? I don't understand this. P is about as concentrated as it can be. Do you mean? But for ordinary macroscopic object, the uncertainty relation is pretty much saturated. The left-hand side is roughly equal to h bar. Why? Ordinary macroscopic objects, the uncertainty relation is pretty much saturated. The left-hand side is roughly equal to h bar. The reason for this are very complicated and I won't go into them here. Instead, let's assume this is true and work out the implication. Strange. So, don't worry. All it says is don't worry. Instead, let's assume this is true and work out the implications. What is delta P? It's m delta V, which gives us m delta V delta X is about h bar. Rearranging the symbols, we can then write delta V delta X is about h bar over m, or delta x is about h over m delta v. Now, if I put a bowling ball on the ground, I know very well that the uncertainty in its velocity is not very big. As the ball gets heavier and heavier, you might expect the uncertainty in velocity to get smaller and smaller. But in any case, the right-hand side has m in the denominator, and regardless of delta v, as m gets smaller, delta x will get bigger. And in particular, it will tend to get bigger than the features in the potential. As m gets I think this is strange, so don't worry. I would say, don't worry. Don't worry. Don't worry. Don't worry. I would say, in the quantum mechanical limit, where m is very small and delta x tends to be big, the wave function will move under the influence of a lagged potential, which it sees as being much sharper and more features than the wave function itself. I don't understand this English. Which it sees. I think this is which wave function sees, which is this lagged potential, which the wave function sees as being much sharper and much features than the wave function itself. Lagged potential. Lagged potential is something like this. I will say this is a lagged potential. That when the wave are sharper and more features than the wave function itself. That's when the wave function breaks up. On the other hand, as m gets very large, delta x gets small. For a large bowling ball, the wave packet might be very concentrated. When it moves through a spiky potential, this tiny wave function encounters a potential whose features are comparatively very broad. Moving through broad, smooth features does not break the wave function into pieces. Large masses and smooth potentials characterize the classical limit. A particle with low mass moving through an abrupt potential behaves like a quantum mechanical system. Okay. What about electrons? Are they massive enough to behave classically? The answer depends on the interplay between the potential and mass. For example, if you have two capacitors plates separated by a centimeter with a smooth electric field between them, then the electron will move across the gap like a nice, coherent, almost classical particle. On the other hand, the potential associated with the nucleus of the atom always has a sharp potential associated with the nucleus of the atom always has a sharp feature in it. If an electron wave packet hits this potential, it will scatter all over the place. Before leaving this topic, I would like to mention minimum uncertainty wave packet. These are wave packets where delta x, delta p is equal to h bar over 2 as opposed to being greater. In other words, in these cases, delta x times delta p is as small as quantum mechanics allows. These wave pockets have the form of a Gaussian curve, and they are often called Gaussian wave pocket. Over time, they spread out and flatten. Such wave pockets are not that common, but they do exist. A bowling ball at rest is a good approximation. In lecture 10, we will see that the ground state of a harmonic oscillator is a Gaussian wave pocket. Don't worry. I would say don't worry. Path integral. Maybe we do this tomorrow. What about that? We do from 3.301. Let's see. Oh, there was he's very nice. And we go to here. Next time, let's see the schedule. Let's see the schedule. SusskindQM. I forgot how to check. Sunday, 9 o'clock. Sunday, 10 o'clock. Oh my god. Sunday 10 o'clock. Okay, so Sunday 10 o'clock. Next time is Sunday 10 o'clock. Okay. Then I put this link to the this is bug, I think.第8回 is here. Yeah. So I copy this and I place it here. Then I do this. 第9回 and part 5. Then we go to 301 path integral. 3月6日更新。Yeah. Okay, so then we also change compass. 編集。part 5。301. Okay, and we do 6. 10 o'clock. 保存. Then we go to number 8. Then we delete. Yeah, I think this is should be okay. Delete. Then we can check number 8. Then no message. No message and only one person is watching. Okay.